All right, today we're tackling one of the biggest puzzles in AI right now, and this is fresh from the latest NeurIPS workshop. The core question is, can our most powerful AI actually think, or is it all just an incredibly convincing magic trick?
I mean, you see it, I see it. AI can write, it can code, it can create stunning images. But here's the question that's keeping researchers up at night. Is any of that actual thought? Is it real intelligence, or are we looking at the world's most sophisticated parrot? So this whole challenge really boils down to this huge gap, right? On one hand, you've got what AI is amazing at today, sophisticated pattern matching. It's like a student who's memorized every single problem in the textbook. But what we want, the Holy Grail, is an AI that can solve a problem it's never seen before, from scratch. That's real deliberate reasoning. And bridging that gap, well, that's the multi-trillion-dollar question.
And this leads us to our first big clue, or maybe it's a red herring. Researchers are calling it the reasoning mirage. The idea here is that one of AI's most impressive abilities might not be what it seems at all.
Okay, so at the center of this whole debate is a technique called chain of thought, or COT for short. And the concept is super simple. Instead of just asking for an answer, you tell the model, hey, show your work. Just like your math teacher used to demand. And what's crazy is it works. Performance goes way, way up.
But, and this is a huge but, here's the twist. The theory is that what looks like reasoning, what looks like the AI thinking through a problem, is actually just the model being a master forger. It's finding bits and pieces of similar logic from its training data and just stitching them together. It's not deduction, it's a super advanced, almost undetectable form of copy-paste.
And the evidence for this is, honestly, it's pretty shocking. Look at this. When a problem looks familiar, the model aces it, near perfect. But the moment you change things, even a tiny bit, it all falls apart. You reverse the logic. They actually call this the reversal curse, and performance just collapses. You add a little bit of random noise, it gets confused. Make the problem just one step longer, the accuracy nosedives. That's not a thinker. That's a brittle house of cards ready to tumble at the slightest breeze.
So what in the world is going on inside that black box? If it's not real thought, what is it? Well, the next phase of this whole investigation is to grab a wrench, crack open that lid, and see if we can find the ghost in the machine.
And the way they're doing this is with a field called mechanistic interpretability, using a technique called circuit analysis. Seriously, just think of it like neuroscientists mapping a brain. They're not just looking at the final answer anymore. No, they're going inside and tracing the exact electrical pathways, the circuits that light up when the model is trying to solve a logic puzzle.
And what they're finding is incredible. It's like there's a tiny, lightning-fast assembly line inside the AI's brain. In a model like Google's Gemma, they've found specific parts that do specific jobs. Step 1, a set of neurons they call rule-locating heads scan the prompt and find the important rules. Step 2, fact-processing heads kick in to check if the premises are true or false. Then, logical operator heads do the heavy lifting, the ands, the ors, and finally, decision heads put it all together and spit out the conclusion. It's a real mechanical process.
And get this is where it gets really mind-bending. They're finding these same kinds of circuits, or very similar ones, in totally different models from different labs. It suggests that reasoning might be a convergent behavior, like how both birds and bats evolved wings independently to solve the problem of flight. It seems like these giant AI models, when faced with logic problems, are independently discovering the same internal wiring to solve them. Wild, right?
Okay, so peering inside the AI brain is fascinating. But the big engineering question is, how do we make them think better, faster, and cheaper? How do we go from this brute force gas-guzzling approach to something way more elegant and efficient?
Well, let's talk about one of the biggest bottlenecks, something called the KV cache. The easiest way to think about it is as the model's working memory, its scratchpad. As it's thinking through a problem, it's writing down all the steps. But that scratchpad gets filled up fast, and the more that's on it, the more memory it eats up. And the whole process just grinds to a halt.
So how do you fix that? The normal way is like using a whiteboard and just never erasing anything. It just gets more and more cluttered. But a new, really clever technique called the rolling window reasoner is more like a smart student. It keeps the original question in the corner of the board, keeps the latest step it's working on, but it erases all the messy middle steps it doesn't need anymore. It cleans up after itself.
And the result? It's huge. This smarter approach gets pretty much the same answer, the same accuracy, while using 50% less memory. For anyone actually paying the bills to run these things, cutting your memory budget in half is an absolute game changer. That's a massive leap.
Okay, so making the model faster is great,
But that doesn't fix another, maybe even bigger problem. How do you stop the AI from generating what people call fluent nonsense? Arguments that sound perfectly logical and convincing, but are just completely wrong.
Well, one really powerful idea is to force the model to ground its reasoning in something that doesn't lie: code. With a method called executable counterfactuals, you don't let the model just talk its way to an answer. Now, you make it translate the question into a Python script. Then an outside program just runs the code. And code is black and white. It either runs and gives you a result, or it breaks. There's no room for fluent nonsense. The verified output is the answer.
So when you put all these pieces together, better reasoning, more efficiency, verifiable logic, you start to unlock the next level: AI agents. We're moving beyond AI that just knows stuff to AI that can actively go out on a mission to find and verify new stuff on its own.
And you can really see the evolution here. We started with basic RAG, which is just a one-step lookup. Then we got early agentic search, which could maybe take 2, 3, 5 steps. But the real cutting edge now is deep search. We're talking about agents that can take 10, 20, or even more actions in a row, exploring websites, running code, checking databases, all to answer a really complex question.
And here's the kicker. The breakthrough isn't just about building bigger and bigger models, it's about smarter training. A new technique called RAPO is letting even smaller, more nimble models, like this Fathom Search 4B, pull off these really complex, long-term tasks. And in many cases, they're actually outperforming models that are way, way larger.
But as these agents get more powerful, we run smack into another really strange puzzle: morality. This recent study found something totally backwards. If you give an LLM a clean, textbook ethics problem, it actually does better than most humans. But the second you add messy, real-world details, irrelevant noise, the AI just completely falls apart. It has no idea what's morally relevant and what isn't. Humans, on the other hand, can cut right through the noise. And for building safe AI, that is a massive gap we need to solve.
So after all that, where are we? Well, the path forward seems to be breaking down into 3 main strategies, all while that one big central puzzle is still staring us in the face.
All right, path number 1. Get smarter about how we use compute to make the AI's thinking process more efficient. Path 2. Ground the reasoning in things we can verify, like code, to stamp out that fluent nonsense. And path 3. Keep mapping those internal circuits so we can build models that aren't just a black box, but something we can actually understand and steer.
But even with all that incredible progress, we circle right back to where we started: the generalization mirage. That brittleness we saw, it's a dead giveaway that today's models are still relying way too much on memorization. Getting them to make that leap to true abstraction, to creating truly new logic, that is still the Mount Everest of AI research.
And that leaves us with one last kind of spooky question to chew on. As we inch closer to building machines that can truly reason, that can think in ways we haven't taught them, we have to wonder: will their way of thinking even resemble ours? Or are we on the verge of creating a new kind of logic, a new form of thought so alien that we humans won't be able to follow it at all?